Hello, welcome to Material Science Lecture. This is our last lesson for Module 7 in which I will continue discussing about heat treatment process for steel. But today I am going to introduce a heat treatment process that involves continuous cooling. So in industrial heat treatment process, in most cases, steel is not isothermally transformed at a temperature above the martensite start temperature, but instead it is continuously being cooled from austenitic temperature to room temperature. So one of the limitations of the TTT diagram is that the transformation, the microstructure transformation, is based on the isothermal processes. Because of this limitation, continuous cooling transformation diagram were developed to overcome the limitation of the isothermal transformation curves. So I'm sure you're not going to understand it now. We're just in the beginning of our lesson, but I hope at the end of this lesson you know what I'm talking about. So let's get started. So as usual, before I start my lesson, I would like to explain some of the learning outcomes that you should achieve by the end of this lesson. So by the end of this lesson, you should be able to understand what is the hardenability of steel and understand how and why Jominy end-quench test is performed, and you will be able to use CCT diagram to predict phase transformation during continuous cooling heat treatment process. I have this very short video clip here that I would like to share with you on how a huge structure of steel being heat treated in the industry. So this is a quenching process in which the structure, the steel structure, being quenched inside water. So I would like you to think how is the temperature differs from the cross-sectional area of this steel product. So as you can see here, another product being quenched inside the water. And what I would like you to think is that what do you think happened in the middle as opposed to the surface of this structure during this quenching process? So in a second, you will see that the steel product being lifted up, and you can see that the materials has been cooled down. So this is what we call as quenching process. So obviously, when this hot steel workpiece being cooled, during this process, the area in contact with water will immediately become cool. So it will be immediately cools down to a temperature of the water itself. However, the inner depth of the material will not cool so rapidly. And in a workpiece that is so large, the cooling rate may be slow enough to allow the austenite to transform fully into other structure other than martensite. So by now, I hope you know that the outside will transform into martensite straight away because we cool it from austenite temperature down to a room temperature straight away. So the outside structure will transform into martensite. But if because of this not isothermal transformation, because this is not an isothermal transformation, you would expect that the middle part will cool slowly as comparison to the outer part. So we could generate other microstructure in the middle. So this is what we call as a structure with shell and core. So this will result in a workpiece that do not have the same crystal structure throughout the entire depth of the materials of the structure. So you might have a softer core such as perlite instead. So that is what happened, or what I meant by continuous cooling heat treatment process. So the rate of cooling of the outside of the steel product is not the same as the inside. So you will expect that these materials will have a different microstructure throughout its cross-sectional area. So in continuous cooling heat treatment process, steel is undergoing continuous cooling as opposed to an abrupt rapid quench. So the transformation of austenite to other microstructure occur over a range of temperature rather than at a single isothermal temperature. So instead of using isothermal transformation diagram to predict the microstructure, we have another diagram that we call as CCT diagram. So this is continuous cooling transformation diagram. So this diagram is used to represent which type of phase changes will occur in a material as it cools at a different cooling rates. So in this lesson, we will look how we construct, material scientists construct this phase diagram. In order for you to understand the phase transformation that happened during the continuous cooling heat treatment process, there is this one material properties that I would like to introduce to you that is very important in order for you to understand the phase transformation. This material properties is what we call as hardenability. So hardenability is a material properties. It is the ability of a metal alloy to be hardened after putting it through a heat treatment process. So in other words, how easy is the steel to be transformed into martensite. So you should not confuse this with hardness. So to give you a simple example is if let's say I have metal A and metal B, and both of them has the same dimension, same structure, it is exactly the same diameter, and now I quench them, okay, and I took it out and I have a look at the cross-sectional area to look at the transformation that happened from the surface to the inside. In metal A, what I observe is that 8 millimeters from the surface, I have martensite, whereas for the metal B, I have only 4 millimeters from the surface that transform into martensite. So I can say that the hardenability for metal A that have 8 millimeters martensite forming from the surface has a higher hardenability than metal B. So that's how, that's just a simple example on how to explain what is hardenability. So how easy is that material can be transformed into martensite. So knowledge about hardenability of steel is necessary to select the appropriate combination of alloy steel and the heat treatment procedure to minimize thermal stresses and distortion in manufacturing component of different sizes. So you can imagine if I have the one that have various microstructure transformation in the cross-sectional area. You can imagine there will be a lot of stresses and distortion generated, internal stresses and distortion generated due to these different phases. So we have to have this knowledge about hardenability in order for us to select which procedure of heat treatment that is suitable for the different type of steel. So in order for material scientists to get these properties, the hardenability properties, they have conducted what they call as Jominy end-quench test. So this is a standard test for measuring hardenability of steel. So this will describe the ability of the steel to be hardened in depth by quenching. So hardenability is depend on the chemical composition of the steel and can also be affected by prior conditioning process such as the austenizing. What is the austenizing temperature? If you heat it up too high, the temperature will need more time to cool down, right? Even though if you quench it straight away, so the inner part will take some time to cool down. So it all will affect the hardenability of the steel. I have a very short video clip here showing how Jominy tests being performed. So these tests involve heat treating a round metal bar of a standard size being transformed to 100% austenite through heating inside a furnace. So as you can see, this steel bar with certain compositions of carbon has been heat treated, and now what they did is they then quench one end of the bar with room temperature water. And as you can see from the clip, that the cooling happened continuously from one end to the other, towards the other end of the steel bar. So as you can predict, the microstructure transformation did not happen abruptly. So you can expect that the microstructure transformation will be differ from one end to the other end. So logically, the cooling rate will be at the highest where the end where the water touch. And this cooling rate will slowly decrease as the distance from that end increases. So what they did after that test is they took out the specimen and they used hardness tests to find the hardness at various distance from where it is being quenched. So we know that the cooling rate will be different at a different distance. So if the material has the higher hardenability, means that it will have the hardness value that is the same or almost the same from the end where it is being quenched towards the other end. Means that at very slow cooling rate, it still can maintain that hardness value. Materials with lower hardenability, it will give a result or a data of hardness that will vary along this the distance, the length of the bar. So for instance, it has one value here and it's slowly decreasing, means that at a slow cooling rate, it transforms into different microstructure. So into different phase or a different microstructure. And therefore, the hardness is reducing. So the hardenability is found for this bar by measuring the hardness along the bar. So you can imagine if you have different compositions of steel bar, it will give you different hardness and it will give you a different hardness value along the bar. So you can compare the hardenability of one materials to the other. This hardness information that varies along the bar is then being plotted on hardenability graph. So here is an example of hardness versus distance of some type of steel. So here the distance is was taken from distance 0, which is the distance where the water quench one end of the sample towards the other end. So as you can see here, the hardness is at the highest where the water quenched the specimen, and towards the end of the bar it becomes softer, so the materials become softer. So here what you can see is when the water touched the specimen with the highest cooling rate, martensite is formed. Towards the end, actually what makes it a bit softer is that there's no more transformation of martensite because the cooling rate is quite slow. Ferrite and cementite, which is perlite, being transformed instead. So if we have materials with higher hardenability, instead what we can observe is something like this. So the hardness from where the specimen is being quenched towards the other did not vary that much. Means that they can still maintain martensite formation towards the other end where the water, the distance from the water quench end is a little bit further up. So that's what is hardenability is all about. So from the Jominy test, the data on the cooling rate at various locations can be also used to construct continuous cooling transformation diagram. So if you're performing heat treatment using continuous heat treatment process, continuous cooling heat treatment process, you need to instead refer to this diagram instead of the isothermal transformation diagram. So how did they construct this diagram? Is that they take the curve of the cooling rate at different location. So here, this is the location where the specimen being quenched. So the water touch this location first. So the highest cooling rate is at that point there. So as you can observe, the cooling rate decrease from that end towards the other end. So what they did is that at different location, they observe when the transformation start and end. So for instance, for this location, the cooling rate is with this curve here. And they observe microscopic observation, the transformation start here and it end here. This is only for eutectoid steel. And for this location, location C, the cooling rate is this dashed line here. And they observe under the microscope the transformation start at that point, transformation from austenite to perlite start at that point and end at this point. So they do at different location and they start plotting where it end and where it started. So that's how they construct the continuous cooling transformation diagram. So if you are doing heat treatment using this method, you need to refer this diagram instead. You might ask me, Madam, they look similar to isothermal transformation diagram. Yes, I agree with you, they look similar. So for eutectoid steel, this is the superimposed of the isothermal transformation diagram, the blue color here. So this is what we learned in the previous lesson. So as you can see here, the curves look similar, but with the CCT diagram, the transformation start and finish are shifted to longer time and at a slightly lower temperature. And also there is no transformation to bainite can be observed for eutectoid steel. So this is the construction for eutectoid steel. So they used a similar technique to construct continuous cooling diagram for the different type of steel with different composition of carbon. I'm just taking the example of eutectoid steel. So again, if you are using this method of heat treatment, you have to refer to the continuous cooling transformation diagram instead. So the CCT diagram for the eutectoid steel will give you the various transformation product which will be obtained at different cooling rate. So the end products are usually martensite or perlite depending on the cooling media. This is only for eutectoid steel. So here is the CCT diagram for the eutectoid steel. This has been polished from what you have seen in the previous slide. So from what you can observe here, if let's say you have a very thin film of eutectoid steel, like a knife or something like that, and if you quench them in water, water will give it a higher cooling rate. So the end product for that thin film, you will get martensite. So your thin film eutectoid steel will be very, very hard. And if let's say you have that eutectoid steel, the same dimension, the same thickness, and you cool them inside the furnace, for instance, means that you are actually performing continuous cooling for full annealing process. So you switch off the furnace and it cools inside the furnace. So what you can see is that the transformation will give you the final product. If you use this diagram, you can predict your final product will be perlite. And the start of the transformation will be after 100 seconds being switched off, when you switch off the furnace. So your furnace, let's say, have this temperature here, which is 750 degrees Celsius. And you turn it off and you leave it there for the transformations to happen. And using this TTT diagram, you can predict that the transformation will begin after 100 seconds and the transformation will end after, say, around 500 seconds. So that's how you use the CCT diagram. So if, let's say, you have the same, again, you have the same eutectoid steel, the same dimension, the same thickness, very thin, and you heat it up to become austenite at 750 degrees Celsius. Now, instead of quenching it in the water, or you leave it cool in the furnace, you take it out from the furnace. So now it's going to continuously cooling from 750 degree to room temperature. So with the air cooling, you can predict that the transformation will start after around 9.5 seconds and it will end at around 50 seconds. So that's how you use this CCT diagram. So again, it will give you full perlite, so fine perlite after the transformation finish. And if, let's say, you want to have a variation of martensite and also perlite, you can quench it in oil quenching instead. So oil quenching, you will start at the transformation from austenite to perlite at around 3 seconds, and the transformation from austenite to perlite would not finish because it doesn't touch any point at the finish transformation line. So this is transformation N, and this is transformation begin. So the rest of the product, the rest of the microstructure will eventually turn into martensite instead. So this blue line here represents the critical cooling rate, in which that for eutectoid steel, if the cooling rate past this blue line, which is slower than this blue line here, you will have a product of perlite and a mixture of martensite. If you have any cooling rate that is higher than that, means that your final product will all be martensite. So that's how you use this CCT diagram. So the hardenability, there are several factors that can affect the hardenability of steel, and these are the carbon content. So if you have the higher carbon content inside the steel, the materials will normally have higher hardenability. So it's easier to form martensite when the steel has a lot more weight percentage of carbon. So you would expect that hyper-eutectoid steel have a higher hardenability compared to hypo-eutectoid steel. And also the other factor is the alloying element, which we'll look into deeper in module 9, and also the austenitic grain size. So just an example how the alloying element can affect hardenability is through this example here. So these are steel that consists of 0.4 weight percentage of carbon. So all of them having this average of 0.4 weight percentage of carbon. How I can tell is looking at this, the last number here. So all of them has a similar amount of carbon, but different steel here has different alloying element. So for example, 4143 has a higher number, 4340 has a higher number, higher weight percentage of chromium and manganese inside it compared to 4140. And this different alloying element will give different hardenability to these two steel here. As you can observe, the 4340 can maintain the hardness throughout its depth. So it doesn't change that much from where it's being quenched to where the other end of the specimen of the Jominy test. However, with the 4140, you can see that martensite formed first based on the hardness Rockwell number, and the hardness number drop after even that distance from where it's being quenched. So it drops, means that the perlite starts to transform and the materials is getting softer from one end to the other. So if, let's say, you have an application which require you to use these two materials, to select between these two materials. So you have 4340 and you have 4140, and you have it in the same thickness and same dimension. Now you want to select which one is the best for your application. If your application requires the materials to be hard and strong throughout its thickness, you will choose this one. So you would expect, if you do heat treatment to these materials, when you quench them in water, at different cooling rate, you can maintain the transformation of austenite to martensite. However, if you select this one, you would expect at a certain location, through the thickness of the material, perlite will be transformed instead. So that's how the alloying element can affect the hardenability of steel. So you quench them in the same medium, have the same carbon, but the transformation will be different throughout the thickness of the materials. And also with the presence of different alloying elements such as chromium, phosphorus, nickel, silicon. So they use different alloying element to give different effect to the steel. So you can observe that, or you would expect that the CCT diagram will look different again. So the transformation will begin at different time. So this is an example of the CCT diagram of the 4340 steel. So as you can observe here, at different cooling rate, different transformation will be observed. And also different with the eutectoid steel just then, that consists only carbon and iron with a percentage of 0.8 percentage. You can observe here with different alloying element being added to the steel, and with the amount of carbon at different percentage, bainite starts to transform as well. So this is just an example. We're not going into further into this. I just want you to know that they at different with different alloying element, with different weight percentage of carbon, you need to use different CCT diagram in order for you to design your continuous cooling transformation or continuous cooling heat treatment process. For a standard plain carbon steel, a continuous cooling heat treatment process will produce common cooling rate along the steel bar of the same diameter. However, these cooling rates differ for different bar with different diameters, and also the cooling rate differs for different position in the cross section of the bar, and if you use different quenching media. So this figure shows bar diameter versus cooling rate curves for different cross-section location within steel bar using different quenching media, which is water and oil. So there are four most common quenching media that will give different cooling rate during the continuous cooling heat treatment process. So the first one is air or compressed air, which will give the slowest cooling rate. So this procedure is being used in a heat treatment known as normalizing. So in normalizing, we continuously cooling after we heat the metal to become austenite. We cool it at room temperature in still air. So that is continuous cooling procedure. So we will produce a coarse microstructure due to the slow cooling rate. and then we have oil. So oil is able to quench heated metal more rapidly than compressed air. So the cooling rate is a little bit higher than compressed air. And then we have the third most common one is we cool metal in water. So water will cool metal more rapidly than oil, and it is non-flammable. And the last one, which will give you the highest cooling rate, is brine. So brine is a mixture of salt and water, and it will give the fastest cooling rate. I'm not gonna talk more on what happened during quenching process, but if you are interested, I have shared what happened during this process. It is not in your syllabus, but if you're curious and you want to know what happened during the quenching process, I have shared the video with you in WhatsApp on what happened during this process. So if you are interested, you can always check out that video. So in summary, for this lesson, we have learned about hardenability. To select a steel for a component that will be heat treated, it is important for us to know its hardenability. We've learned that Jominy and quench test is used to determine the hardenability of metals. Even though you did not perform the experiment by yourself, at least you have some idea on how metal hardenability been determined. And also we have learned how CCT diagram is constructed using data obtained from Jominy and quench test. And we also learn about the heat treatment procedure for steel and how it can be formulated using CCT diagram to obtain the desired microstructure. So that's about it for this module, module 7. I hope I have given you enough insight on one of the most important materials for mechanical engineering, which is steel. So steel is being used in a lot of mechanical engineering application where it's being used to manufacture parts such as valve, shaft, axles, and also sprockets. Where it is being designed by mechanical engineers. And also this materials is being used extensively in structural engineering. And also we've talked about how we can heat treat these materials to change its behavior, mechanical behavior. So that's about it. I'll see you in class. Thank you very much.